Now we have the tricky stuff. So tabular integration is great for certain types of problems, but not necessarily all integration by parts problems fall into that category. Like mentioned in the last video, the point is with polynomials that you're differentiating, they eventually go to 0 because they eventually go away. That's how polynomials work. If you don't have a polynomial there, that last integral matters. So to properly solve these problems, you have to write out that last integral so you actually be able to work it out and solve the problem. Now the problem here is, as a whole, for most of these problems, tabular integration doesn't have an end, right? You can just keep differentiating, keep integrating as far as you want. So there is no real last integral, so you have to know, based on the problem, based on what you see, when to stop doing this process to get to a last integral that's useful. And that's where the sort of tricky and the complications for this process come about, is knowing when to stop the process to get to a point that's actually useful for solving the rest of the problem. We'll have two examples here of these situations. One that I call circular integration by parts, where one that the goal is to wrap around to where you started again and get the answer that way. And the other one is when you have a term like a log or inverse function in there, where you have to differentiate that and not the polynomial, being able to figure out how you actually go forward from there. Both of those can be done via this method, but they're more complicated because of how you have to set up the last integral. First of these is a circular version, and it's something like this, integrating e to the 2x cosine of 3x. Now you may have seen this via normal integration by parts. Basically the point is, if you integrate by parts on this twice, you will land back at an integral that looks like e to the 2x cosine 3x with a constant in front, move to the other side, solve it out that way. That's how this problem is normally solved. All right, so normal process is integrate by parts twice, and then move things around to solve for the integral. So how does this look in tabular integration? Let's just say, for the sake of this, let's make our table. I'm going to differentiate e to the 2x and integrate cosine of 3x. You can do this either way, and the answer is going to be the same no matter what. I will just do this method for the sake of this example. So let's fill the table. Let's go at it. Differentiating is fairly straightforward. I get 2e to the 2x, and the pattern keeps going. And I can integrate cosine as well. Integral of cosine is sine. I get a 1/3 from u sub in there, and I can keep going that way as well. Here's the problem with this setup. Neither side here ever stops. I can just keep going and differentiate integrating over and over and over and over again, and I will never get to 0. Right? This process never ends. So if I want to actually get to an answer here, I have to know where to stop this to get something useful. And the main point here is that the last term is an integral built straight from a horizontal line across the table. So in order to solve this problem, I want to find a horizontal line that looks like my initial integral up to some constant. What do I mean by that? So my original integral looks like e to the 2x cosine 3x. I want to find those terms on a horizontal line somewhere in my table. First line, not useful because that's the original problem. But what I see in line 3 is an e to the 2x and a cosine 3x. So if I did that as an integral, it would look like the original problem. So we are going to stop the table there and see what we get. So put in my plus and minus signs, and let's write out the answer. So this says that, based on tabular integration, integral of e to the 2x cosine of 3x dx equals first term of e to the 2x times a 1/3 sine of 3x minus second term, the 2 e to the 2x times a negative 1/9 cosine of 3x, and then plus integral from this last row, 4 e to the 2x to the negative 1/9 cosine of 3x dx. If I collect my terms a little bit, I will see this looking like 1/3 e to the 2x sine of 3x, a plus 2/9 e to the 2x cosine of 3x, and then a minus 4/9 integral of e to the 2x cosine of 3x dx. And that equals integral of e to the 2x cosine of 3x dx. I can now play the same trick we do normally and move this integral the other side, combining those two fractions to get that 1 plus 4/9 is 13/9. Integral e to the 2x cosine of 3x dx equals 1/3 sine of 3x plus 2/9 e to the 2x cosine 3x. And I get my answer by multiplying both sides by 9/13. So I won't write out here, but multiply the other side, and that'll give you the final answer here. The ending here is the exact same as it is by normal integration by parts, because it is the same process. We're still doing integration by parts, just with a different technique to show you how to set it up. And so that'll work, but you have to know when to stop the table. Because the table never stops, you have to pick a place to do so. This would work. You could also stop it down here. That line also works, but that's more steps and more complicated process to solve up the answer. First one's the best one you want to stop with. And so if you can figure that out, you can use this for these problems. I'll have recommendations in the next video, but I'd recommend actually doing this via normal integration by parts and not tabular to make sure you don't stumble over this block of when to stop the table. The second type of problem here is one where you don't differentiate a polynomial. I guess the first one was like that too. This is sort of a more general version, but this also shows up too. Something like x squared log of x dx. Now, based on my rules, I want to differentiate the log and integrate the x squared. The main point being, we don't have a nice formula for integral of ln of x. Even if we did, and we do, it's more complicated than just log of x itself. And you're not going to get towards an answer if you do it that way. So this causes problems, as you can imagine. The problem here being, if I set this up the way that I should, with differentiating natural log and integrating x squared, again, neither process stops. Root of ln is 1 over x, so x to the minus 1. I can keep going here, and then 1 over x squared, or x cubed, and so on. And we're integrating x squared, that's going to just go up and up and up forever. So again, a process that never stops. As you'd probably guess, the trick here is knowing when to stop it to get something you know how to do. And the trick or the point here is, again, the last step is always a horizontal integral across the row of the table. And when doing that integral, you're allowed to combine terms across the columns, but only in the final integral. Because what do? Well, I multiply them together and then do the integral. So if that multiplication helps me do things, I can move terms back and forth to make it easier to solve out. And so the key point here, and I'm going to mess up this table now for the sake of this example, is that at this point here, I could combine terms. And I could rearrange this product here of 1 over x times x cubed over 3 as 1 times x squared over 3. Right? I basically move the 1 over x into this side for the sake of the final integral. And it's greener because it's not really a part of the same table, but it means that I can now use my structure of integration by parts in tabular integration to then solve this out. If I want to, I could take this and take the one more step to write this as 0 and x cubed over 9. But I need to realize that when I'm pairing this, I have to pair blue with the blue and green with the green. I can't pair across the lines. I did a recombination there to make this nicer. So if we do it this way, we can see that there are a couple ways to get the answer from this table. Part 1, I have integral x squared log of x dx. I can do my first step, which is this and this term with a plus sign up here, to give me this x cubed over 3 log of x, and then do the integral across minus integral of 1 over x times x cubed over 3 dx, which this becomes x squared over 3, which I then know how to integrate directly, x cubed over 9. Or if I want to use my recombined table, I'll keep this minus sign here, and I'll have one more term that is this 1 times x cubed over 9, and then the 0 here gets me my plus c again, which that'll give me exactly the question that I had below. So either idea works for this. If you want to build this in a table, you can. Again, this is the recommendation that I would have, is to not do this in by tabular and do it just by integration by parts normally, because it's going to be a lot easier to see how it comes together if you don't have to remember to combine the terms together across the integral when it needs to show up in the problem. So there's more complicated problems for integration by parts that really aren't the best solved by tabular integration. It works great for its one particular use with polynomials being differentiated, but besides that, it can be a little more tricky to see how to actually work out the process to get to a final answer when you use tabular integration for these problems. The next video and last one in this set will be recommendations for when to use which method for solving out these types of problems that you see on exams or in your life or wherever you see these problems come about.